Okay, this is a video for Adam, but also for all the other students who are wondering about this index notation. Index notation used to be a component of the course. It's been moved to the appendix. You don't have to know any of this, but it's just useful for you to know for your other courses. So index notation provides an easy way of doing a lot of the vector calculus proofs. It's based upon two principles which I'll present here. The first principle is that if you see a double index, then it means summation. So for instance, if I have A dot B, I can think of this as AI BI. You see the double index I here, and it means you sum over all the I. So I runs from 1 to 3 if it's a vector in 3 space, right? So index notation profits from the fact that you don't have to write down these sigmas every single time. You just think of it as I see a I and an I here, and I have to sum over 1, 2, and 3, okay? The second principle that you use is this. So if you see epsilon ijk here, then this takes 3 possible values. It's either 1 if it's cyclic, 1, 2, 3, or 3, 1, 2. It's -1 if it's acyclic, or it's 0 if it's repeated. So in other words, you see 3 numbers that appear for the ijk here, and if you read the numbers in the order from left to right, if they're occurring in the order 1, 2, 3, so 1, 2, 3, or 1, 2, 3, and so forth, then it's 1. If it occurs in not that order, 1, 3, 2, or 1, 3, 2, and so forth, then it's -1. And if it has at least one repeated digit, so 1, 2, 1, 1, 3, 1, 1, 1, 2, 1, 1, 3, etc., then it's 0. Okay? This definition allows you to define the cross product. So you would write the cross product A cross B. The ith component of the cross product is epsilon ijk aj bk. Okay? The ith component is epsilon ijk aj bk. You always remember these two indices are the second and third index of the epsilon that appears. So you see the 2 repeated indices, the j's repeat and the k's repeat, and that means that there's 2 sigmas in this. You have to sum over all j's and over all k's. So you should rather write this with 2 sigma signs, but you write it in this way because it's more convenient. You don't sum over the I is a number that you choose. So let's just do an example together. If I try to get the first component of this cross product, I would write down epsilon 1jk ajbk and sum over the 3 possibilities for j and the 3 possibilities for k. But I also know that epsilon ijk is 0 if any of the later j and k numbers repeat. In other words, I only have to include the unique combinations of ijk or 1jk, and there are only 2. There's epsilon 1, 2, 3, a2, b3, and there's epsilon 1, 3, 2, a3, b2, because all the other ones will include a repeating digit. Right, now epsilon 1, 2, 3 is 1 because it's cyclic. You count from the 1 and you count from left to right, so 1, 2, 3. And this one is acyclic because it occurs in non-cyclic order. So this one's a 1, this is a -1, so this is a2, b3 minus a3, b2. And you have the formula for the first component of the cross product. Okay? Now this seems a bit strange. Why would you do all of this when you have other formula for the cross product? And the idea is that by writing it in this way, the epsilon ijk, you can take an advantage of the symmetries of the cross product. And this allows you to make a variety of proofs in a very compact way. I'm going to show you one possible proof that you can take advantage of these 2 guiding principles. The first is that if you see a repeated digit I, it means summation. You sum over all the possibilities of that repeated digit. And if you see this epsilon ijk, then you have to break it down into either cyclic, acyclic, or repeated. Okay, so I'm going to give you one example. We're going to do the triple scalar product, the proof of the triple scalar product, and you can see how short you can make it by using these rules. Okay, so the triple scalar product is A dot B cross C. These are all 3 vectors. is equal to, as long you keep the order C dot A cross B, then, and there's another one where you shift it over by one more. So the triple scalar product says that this equality is true, and you just have to remember, you can always remember it by reading it from A onwards. So A, B, C, and it keeps the positive sign. If you screw up the ordering, then this becomes a minus sign. Okay, so how do I prove this? Well, you first work with the left-hand side. I write the left-hand side as AI, B cross CI, and again you see the two repeated indices, I and I, which means this is A1, B cross C1, plus A2, B cross C2, plus A3, B cross C3, which is the dot product. Then you write the definition of the cross product in terms of that funny notation, the epsilon ijk. This is AI, epsilon ijk, bj, ck. Okay, and when you see this thing, this is actually two summation signs because there's a repeated j and there's a repeated k. Sorry, there's actually three summation signs. There's a repeated I, a repeated j, and a repeated k. But you're free to manipulate this as a product. So I can move the ck over to the left here, and I'll put the rest in a bracket like that. Okay, now look at what I want. I want to write it as a dot product between two quantities. So if I can write this as a ck times something k, then I'll have the dot product. And I want that something k to be a cross product of A cross B. So all I would need to do is change this from an epsilon ijk to an epsilon kij, and then everything works. Am I allowed to do this? Well, this is where that cyclic and acyclic property comes into play. Ijk represents any numbers, any possibility of numbers that you put in, right? But whatever numbers you put in, if you shift it in this way, then it remains either cyclic or acyclic, or 0 if it's repeated. So for instance, if I was 2, j was 1, and k was 3, then this is now shifted to 3, 2, 1, and the order remains the same, and so therefore the value of this epsilon remains the same. So you're allowed to shift it in this way without incurring a negative sign. So this is now A cross B, the kth component by definition, and then this is ck, which is just the dot product by that repeated index notation. Okay, so this shows you how to prove the triple scalar product without going through all that heavy machinery of the cross product. You just use these neat properties of these epsilons ijks. If you'd like to learn more about it, you can read the appendix of the lecture notes, which has more details in this. Again, this is not something you have to know, but this is sort of tricks that often physicists use to reduce the amount of calculations that they have to do for these types of vector proofs. Thank you very much.